Okay.
Yeah, Bhaskar, over to you. You will be chairing the session. Go ahead. Yeah.
Okay. So it's a pleasure to welcome Dr. Kaneenika Sinha from ISA Pune for today's first talk, at least in this session. And she will be speaking on central limit theorems and number theory and graph theory. Kaneenika, please go ahead.
Yeah, thank you, Bhaskar. Thank you to the organizers for giving me an opportunity to present some recent work. So I want to talk about central limit theorems in number theory and graph theory. Most of my ISER colleagues have seen numerous talks on central limit theorems in number theory. So I hope to show you something different today. The motivation for this work goes back to a paper of Serre in 1997. And this paper was a very beautiful paper with some very neat and elegant ideas. So first of all, the main contribution of the paper was that Serre proved an asymptotic distribution result for the eigenvalues of the Hecke operator T sub p acting on spaces of modular cusp forms of weight k and level n. So here p is a fixed prime and n plus k goes to infinity under the restrictions that k is even and p and n are coprime. So this can be interpreted as a vertical variant of what is famously known as the Sato-Tate distribution. So in those days, the Sato-Tate distribution was merely a conjecture, and there was lots of interesting work around it, interesting variations of the problem, and this was one of them. Now, one very important contribution in Serre's paper is that he brings together some classical principles of equidistribution, or what he calls asymptotic distribution of families in compact intervals of R. So these principles were known classically, but he brings them together, states them explicitly, and uses them to derive distribution results for eigenvalues of Hecke operator, as well as eigenvalues of families of regular graphs. In this way, he highlights thematic similarities between these two families, and this is the starting point for the work that we want to discuss today. So here are the general principles in a nutshell from Serre's paper. So let us take any closed interval in R with a probability measure mu. We consider families lying in this closed interval, omega, in such a way that these are finite families, but their size goes to infinity as the index set capital V goes to infinity. And we let C of omega comma R denote the set of all continuous functions on this omega. So we say that these families are equidistributed with respect to the measure mu, or to say it shortly, mu equidistributed, if for any continuous function on omega, the average value of the function as we run over all the lambdas lying in A sub v converges to the integral of f with respect to the measure mu. This is true for, if this is true for every continuous function, we say that the families are mu equidistributed. Now, an equivalent criteria for this is as follows. If something is true for all continuous functions, then it will also be true for all functions which can be approximated with the help of continuous functions. So if we take any interval lying in this omega and we talk about the characteristic function of that interval, the above expression ends up measuring the proportion of the elements in your family which also lie in the interval I, and this converges to the integral of mu with respect to the interval I. So this is an equivalent criterion. And another equivalent criterion which we exploit a lot, and Serre also essentially exploits this criterion to prove his equidistribution results, is that suppose you want to show something for every continuous function on omega, it is actually enough to show it for all polynomials in omega. And if you want to show that something is true for all polynomials, you essentially can just choose a sequence of polynomials, let's call them P sub n, each is of degree n, and just show this equidistribution criterion for these polynomials, P sub n. So these are the three different ways of expressing equidistribution, and Serre's results are an interplay between these three principles.
One question.
Sure.
So your omega is always a bounded interval. Is that right?
Yes. Yes. Yeah, I should have said that. A compact interval.
Okay.
Okay, so in particular, P sub n, you can choose them to be Chebyshev polynomials. So what are the Chebyshev polynomials? These are expressed as follows. So if you write y to be equal to 2 cosine pi theta, let's say y is something that lies in the interval -2 to 2. In particular, if you are talking about the interval -2 to 2, you write y to be equal to 2 cosine pi theta. And this nth degree Chebyshev polynomial, there's a typo here, I meant to say n, is this expression sine of n plus 1 pi theta over sine pi theta expressed in terms of 2 cosine pi theta. So it is not very difficult to verify that for every n greater than or equal to 0, x sub n is actually a degree n polynomial, and we also know its expansion in terms of y. We also denote, this will be helpful for us later, we take for every n greater than or equal to 2, we denote z sub n of x to be equal to x sub n of x minus x sub n minus 2 of x. So let me quickly go over the classical results on equidistribution for Hecke operators acting on space of cusp forms. I won't take very long here, and then we'll soon move to graph theory results. So here is our situation. Here's our notation. Let k and n be positive integers with k even, and let s sub k of n denote the space of primitive cusp forms of weight k with respect to gamma naught of n. And these are in fact finite dimensional spaces over the field of complex numbers, and let s sub k of n denote the dimension of these spaces. Dimension formulas for these spaces are well known, and in particular what is of relevance to us is that these dimensions keep increasing as k plus n goes to infinity. So when I say k plus n going to infinity, I mean that I can either fix k and let n go to infinity, or I can fix n and let k go to infinity, or I can let both go to infinity. In any situation, the dimension just increases to infinity. Now, on these spaces, we define the nth Hecke operator. I'm not going to give you the definition here, so we just denote these by T sub n. So these are certain linear operators on the family, on the space of primitive cusp forms. And by the Ramanujan-Deligne bound, we know that if you have a prime p which is co-prime to the level, then the eigenvalues of T sub p lie in this particular interval, which is parametrized by the prime p and the weight of the space that you're taking. In particular, we can consider the normalized operator, where we take the Hecke operator T sub n and divide it by n raised to the k minus 1 by 2. And now, irrespective of whatever your prime is, the eigenvalues of Tp prime lie in the interval -2 to 2. And so now we can ask questions about equidistribution of the Hecke eigenvalues in the interval -2 to 2. Now, we also denote the set of Hecke new forms in our space Sk of n by f sub k of n. And what are the Hecke new forms? So these are basically the set of eigenvectors, which are simultaneously eigenvectors for all the Hecke operators. And in particular, a Hecke new form has a Fourier expansion where the nth Fourier coefficient is basically the eigenvalue of an eigenvalue of T sub n corresponding to the eigenvector f of z. So basically, a new form gives us a way to list out all eigenvalues. It puts them inside an eigenvector which has this following Fourier expansion. So now we come to the some important results about distribution of Hecke eigenvalues. So Serre, one of the key results of Serre's paper, which actually goes back to a previous work of Sarnak in 1984, is the following. And Sarnak basically proved this result in the context of what are called primitive mass cusp forms. But here is the result. So let us fix a prime P and let AP of Nk denote the family of eigenvalues of these Hecke operators acting on S sub k of n. And Serre shows that these families, A sub P of n comma k, they are equidistributed in the interval -2 to 2 with respect to a certain measure, which is actually a probability measure on the interval -2 to 2, and it depends on the prime P. So now what we do is, now we try to just focus on this result and try to interpret this result in a probabilistic way. So what we now do is we choose an interval I lying in the interval -2 to 2, and we denote mu of I to be equal to the integral of mu of t dt with respect to the interval I. Here mu of t denotes the semicircle distribution measure, or what we also like to call as the Sartor-Tate distribution measure. So now what we do is we take our set of Hecke new forms and treat them as probability spaces, equipping them with the uniform probability. And we define for each prime P, define y sub P as the characteristic function at A sub f of P. So this is equal to 1 if your A sub f of P lies in the interval I and it is 0 otherwise. So once you define a random variable on this space in this way, then it is natural to ask questions about the behavior of this random variable. So we ask questions about its expected value, its variance, and so on. So the expected value of y sub P can be expressed as this, this expression here. So you are summing up over all the Hecke new forms and you're taking chi sub I of A sub f of P. So basically you are counting the number of Hecke new forms for which the pth Fourier coefficient lies in the interval I, and dividing it by the total number of elements in f sub k of n, which is just the dimension of that space. And we also see here that the variance here can be expressed in terms of this variable y sub p of f minus its expected value. You square it and then you take the average of this over all the f lying in your set of Hecke new forms. So now the question is, are these, so we ask a probabilistic question, are these random variables y sub p as you index over the primes well behaved enough so that their sum leads to some kind of a central limit type of a theorem. And this was what was answered by me and Neha. So this was Neha's PhD thesis a few years ago. But before that, we read a lot of literature about equidistribution of Hecke eigenvalues. And basically, many of these results can be interpreted in this probabilistic framework as follows. So if your families, so now what we do is we just take, for simplicity, capital N equal to 1. So we just consider level 1 forms and we let the weights grow very fast, parameterized by the growth condition log k by log x goes to infinity as x goes to infinity. Then a famous result of Conrad, Duke and Farmer, which was later sharpened by Nagoshi, tells us that under this growth condition, the expected value of the sums of the random variables y sub p is asymptotic to pi of x times the Sartor-Tate measure of I as x goes to infinity. And Neha and I built upon this work. So, but to find variance and a central limit type of theorem, we ended up requiring stronger growth conditions on our families. So now we require log k over root x log x going to infinity as x goes to infinity. You will see that this is a far stronger growth condition than the one that Conrad, Duke, Farmer and Nagoshi took. And under these strong growth conditions, we show that the sum of the variances of sigma sub p, the variances sigma sub p squared, they converge to pi of x times mu of I minus mu of I whole square, whereas I just mentioned mu of I refers to the Sartor-Tate measure of the interval I. And with this estimate, asymptotic estimate for the variance in place, we were able to derive a central limit type theorem. So we take the normalized random variable of the type that I just mentioned here, summation yp minus mu sub p, normalized by the square root of the sums of the variance sigma p square. And we show that under the growth conditions that we mentioned, the rth power moments of these converge to the rth power moments of the Gaussian distribution. So these normalized random variables, in fact, asymptotically converge to the Gaussian random variable. Okay. Now, our motivation was, again, the result of Nagoshi in 2006 in the same paper where he talked about average values. So he showed that if you just take, instead of taking the random variable to be chi sub I of a sub f of p, if you just take a sub f of p, so this is no longer a Bernoulli random variable, but if you take this sum of these a sub f of p's and you normalize it by square root of pi of x, these converge to the normal distribution as x goes to infinity. So many of the combinatorial ideas that we took were inspired by the work of Nagoshi, but we had to be more careful because now we are talking about the characteristic function. And more generally, later in joint work with Stefan Bayer, we did something nicer in the sense that we classified a set of test functions which are given as follows. So let g of t denote a certain linear combination of the Chebyshev polynomials x sub 2m of t, where these coefficients u of m are well behaved. I will explain it more in detail later when I talk about corresponding results in graph theory. But for now, it is sufficient for us to know that these grow in a very controlled manner. And in fact, they seem to satisfy like something like a sub-exponential decay. So alpha and omega are just any fixed positive real numbers of your choice. And let's say your coefficients u of m are bounded by e raised to the minus alpha m raised to the omega. With this in place, we modify our random variable to g of a sub f of p. So instead of taking chi sub I of a sub f of p, we are taking the value at this test function. And we showed that under much weaker growth conditions for the weights, we can derive a central limit theorem for these modified smooth random variables. So this was our theorem. Now we move to eigenvalues of regular graphs. So let us now take g of m comma d to be the collection of d regular simple undirected graphs on m vertices. And I'm going to just choose d to be something that is greater than or equal to 3. So we consider the adjacency matrix of such a graph. So what is the adjacency matrix? It is an m by m matrix where the ijth entry is 1 if your vertex vi is joined to vj by an edge and 0 otherwise. And we observe that since we are taking undirected graphs, this is symmetric and therefore it only has real eigenvalues. These eigenvalues are called the eigenvalues of x. Now the adjacency matrix and the operator that is defined by this adjacency matrix plays the role of the Hecker operator p sub p in the situation of graphs. And this is the analogy that we build upon. So some basic facts about these eigenvalues. It is very easy to see that if you're talking about a d-regular graph, then d itself is definitely an eigenvalue of this graph x. And if this graph x is bipartite, then minus d is also an eigenvalue. So in general, any eigenvalue of the form minus d or d is what we refer to as a trivial eigenvalue of x. And we define lambda of x, which is also known as the spectral radius of your graph x, to be the maximum of the absolute value of non-trivial eigenvalues of your graph x. So now what we do is, just like we normalize the Hecker operators, we also normalize our adjacency matrix. So we now consider 1 over root d minus 1 times the adjacency matrix, and a of x, which is the family of eigenvalues of this normalized matrix, is contained in the interval minus d over square root d minus 1 to d over square root d minus 1. And now what we do is we denote the spectral radius of this modified operator to be lambda of x. And a very famous result of Friedman in 2008 shows that if you are choosing x uniformly at random from your collection of D regular graphs with m vertices, then for any epsilon greater than 0, the probability that the spectral radius of the graph x is greater than 2 plus epsilon converges to 0 as m goes to infinity. So here D is a fixed degree and we are allowing our m to grow to infinity. So what this is actually saying is that your non-trivial eigenvalues of the adjacency matrix seem to club around the interval -2 to 2. And in a limiting sense, they actually are in the interval -2 to 2. Let me explain this more. We explain this with the help of some equidistribution results. So we choose a sequence x sub m of graphs such that x sub m lies in this family that we started off with. The question is, for a fixed D, how are the families A of x sub m distributed as m goes to infinity? And we also ask a more general question. Instead of fixing D, how about we also allow the degree D to grow along with the number of vertices? So in this scenario, how are the families A of x sub m distributed as m goes to infinity? What kind of growth conditions on D will help us to get good distribution results? So this question has been very well studied by people in graph theory. In particular, there is a very famous theorem of Mckay from 1980, which says the following. So let us fix a D and let x sub m lie in this collection of D regular graphs on n vertices. And we choose x sub m. So for every m, we are choosing some x sub m in this collection. And we are choosing our collection in such a way that the number of cycles of length n, it is little o of n as m goes to infinity, and this asymptotic is true for every n. So under this strong condition, Mckays showed that the family of eigenvalues A of x are equidistributed in the interval -2 to 2 with respect to this distribution measure. So now, of course, you will ask the question that our eigenvalues, in fact, they don't necessarily lie in -2 to 2. They seem to lie in intervals which contain -2 to 2. And this is one of the amazing things of this result. You can actually take your D is fixed. If you take any continuous function in this interval omega sub D, which is parametrized by your D, then Mckays result is telling you that the average value of any continuous function as you run over all the eigenvalues is asymptotic to the integral of f with respect to this measure, but this integral on the right-hand side is with respect to the interval -2 to 2. So you can start with any D, but as m goes to infinity, this whole thing converges to the integral of f with respect to this measure in the interval -2 to 2. And we'd also like to observe here that if your D is equal to p plus 1, then you end up recovering the equidistribution measure, the vertical Sartor-Tate equidistribution measure proved by Sarnak and Serre. So now we express our eigenvalue statistics and questions related to them in the same language in which we discussed our questions about eigenvalues of T sub P. So what we do is, for some real valued function on R, we may define a random variable B sub F on this collection G of M comma D as follows. So now what we do is we take F of lambda and sum it over all the eigenvalues lambda lying in A of y. So this is our random variable. It is not just f of lambda for some particular eigenvalue, as was the case when we were looking at modular forms, but here this is in fact the trace. So the sum over all the eigenvalues. So a famous theorem of Dumitriu and Paul, which they proved in 2012, addresses the question of distribution as D also goes to infinity along with the size of the graphs. So subject to this restriction that d of m grows to the order of m raised to the epsilon sub m, where epsilon sub m is something which is little o of 1. So it goes to 0 as m goes to infinity, but m to the epsilon m must go to infinity as m goes to infinity. Under these conditions, the expected value of your random variable b sub f is asymptotic to m times the integral of f with respect to the Sato-Tate measure mu. So it's interesting that both Serre's distribution measure as well as the Sato-Tate measure show up verbatim when we talk about distribution of eigenvalues of regular graphs. In particular, for an interval I lying between -2 to 2, the expected value of b sub chi sub I, where chi sub I denotes the characteristic function of the interval I, is asymptotic to m times mu of the measure of the interval I. So these are asymptotics, and now we can ask final questions about variance of these random variables. So Tobias Johnson in 2015 proves the following theorem. So he takes a set of test functions, which is more general than the one that we took in the study of modular forms. So he takes an entire function of finite order. And in particular, what this means for us is that it can be expressed as this infinite sum, infinite linear combination of these Chebyshev polynomials, sub k of x, where a sub k's grow in a suitable manner and in such a way that if you take the a sub k's themselves, the series of a sub k square is absolutely convergent. So what he showed was that now suppose you allow your degree to grow slowly enough so that log m over log d goes to infinity. As m goes to infinity, then with respect to this function f, you have a central limit theorem. So expected value, we already know by the work of Dumitriu and Pal. So you can generalize, Johnson obtains results for the variance, and he also obtains a central limit type theorem for these. But notice, so the growth conditions here, so this is sort of analogous to the growth conditions that we were looking at when we talked about eigenvalues of Hecke operator. So here the growth conditions are characterized in terms of how D behaves in terms of M. So what this growth condition is basically telling you is that if D grows in such a way that it is of the order of some power of log M, then you have these you have the central limit theorem. So now the questions that we ask are, can we obtain asymptotics, the expected value, the variance, and central limit type theorem under looser growth conditions for D in terms of M, possibly for a more restricted class of test functions? So this is joint work with my colleague Moumanti Podder, who joined IISER Pune a few months ago, and we started discussing this. So what we do is we take basically a class of test functions, which we define as follows. So here we basically, for any capital L, we are taking test functions, which are linear combinations of the Chebyshev polynomials x sub 2m of t, where the coefficients u of m depend on the Fourier transform of certain suitable test functions, which have, in fact, we are choosing test functions where the Fourier transform has compact support. And basically what is happening is that now in the test functions that we are taking, these are actually finite combinations. So unlike Johnson's theorem, we are taking polynomials of this form where your m goes all the way up to L. You can start with any L greater than or equal to 1 and write down a polynomial of degree at most L in this way, and try to see if you can derive a central limit theorem for these restricted test functions. So we have some partial results in this direction. We have not been able to obtain a central limit theorem so far, but what we observed was very interesting. So first of all, it allows us, taking this class of test functions allows us to loosen our growth conditions on D. So instead of allowing D to grow as a power of log m, where m is the number of vertices, we are now allowed to let D grow as a power of m, so of the form m to the theta, where theta is something less than 1. So this is a far better condition for the growth of D. And under these conditions, we are able to derive that the expected value of the random variable b sub h sub l is asymptotic to m times the integral of h sub l with respect to mu of t. So this is an analog of the result of Dumitrio and Pal, but with better growth conditions, since we are taking a more restricted class of test functions. And in fact, what we have is something finer. If you take some m, so you are starting with any capital L of your choice, take m large enough so that it is greater than or equal to 2l raised to the power of 10. So we are making this result explicit now. And let d be something which is less than or equal to m raised to the 1/3. Then we can convert this asymptotic result into an effective result with error terms. So the expected value of b sub h sub l is equal to the asymptotic integral plus O of m times log d by log m. So this is an explicit error term, and the implied constants here are absolute and effectively computable. So what next? Now this is work in progress. We are now looking at variance in these calculations, and we want to know if we can find suitable growth conditions for D, under which we can in fact find a central limit theorem for these random variables. So I'm running out of time, so I will just briefly mention the main tool that goes into the study of the distribution of eigenvalues. So just like in the case of modular cusp forms, the main tool was what is called the Eichler-Selberg trace formula. Here we have a formula for the trace of these the eigenvalues of these normalized adjacency matrices. And it turns out the traces here can be expressed in terms of very explicit quantities related to the graphs, families of graphs that you are taking. So given a graph y, let f sub n of y denote the number of closed non-backtracking walks of length n in y, and let c sub n denote number of those non-backtracking closed walks in which additionally the first and last edges are distinct. Then if you apply the Chebyshev polynomial to lambda, x sub n of lambda, and you sum over all the eigenvalues lambda, this trace can be expressed in terms of the number of closed non-backtracking walks. And so this helps when you are trying to apply Serre's general distribution principles to x sub n, to this family. The set of polynomials, degree n polynomials that you can take are x sub n, or in fact, as our calculation goes ahead, it turns out that it is easier to in fact just take x sub n of x minus x sub n minus 2 of x, because this enables us to express the trace in terms of these more restricted closed non-backtracking walks. So this is a beautiful formula, and when we talk about averages and asymptotics, it is just a whole lot easier to play with this formula. So since I've run out of time, I will stop here and maybe take questions.
All right, thanks, Kaneenika. Are there any questions?
Now, one question.
Yes.
Hi, Kaneenika, this is Manjunath. Can you go back to your theorem with Moumanti that you showed?
Just 1 second. Why is this slide mode not moving? Yeah.
So why did you say D can go like a power of m? It looks like you need log m by log d goes to infinity, right?
Yeah, so what this means is that m grows faster than any power of D.
Okay. So D can't be a power of M. Okay. Yes.
Yeah. I mean, it can be a power of M, but it should be less than M. I mean,
Why? I mean, if it's square root M.
yeah, maybe I should be a little more precise here. Yeah, okay, so how about I just write, instead of this growth condition, it would be better to just write D to be bounded above by a certain power of M. So M to the theta, where theta is something less than 1.
Okay.
Then this asymptotic holds. But for us to have the explicit error terms, we need our theta to be less than or equal to 1/3.
So the first statement is valid then for something more than this, right? Some power larger than 1/3.
Yes, thank you for pointing that out. I should just write D is M to the O of M to the theta, where theta is something less than 1.
Okay, thanks.
Thank you.
Okay. Any other questions? I saw somebody else raise a hand. Raise your hand.
Kaneenika?
Yeah, Neha.
Yeah, but for your error term, if you want that to go to 0, you would need, is D being M to the theta enough? Because then, I mean,
Yes, because now D is less than or equal to M to the 1/3.
Oh, okay, okay.
Yeah.
Okay, sure. Yeah. Okay, and for your the variance thing, it's work in progress, I understand. But do you expect a similar the log M over log D, or the expression of D as a power of M being enough, or would you?
Yes, we expect to have the same growth conditions.
Okay.
But it's just the variance calculations are a little more involved. We are still working with them. But we do expect, we basically expect to have an analog of Johnson's result, but with better growth conditions.
Yeah, certainly the D can grow faster probably for our more restricted class of functions. Because when Toby was working on this, Toby actually had some log M to the power something was the condition that he had, which is, I mean, still growing, but not as fast as we would like. So we would like to push that as far out as we can. So yeah.
Okay.
But the point that the previous question, I think Neha made is correct, right? For the error term to be little o of M, you still need D to be not a power of M, but smaller than that. Here in the last statement.
Yeah, so yeah, I basically this asymptotic,
you need that here.
I just need D to be M to the theta, where theta is something less than 1. This asymptotic will still work. But if, no, sorry, theta less than or equal to 1/3, then this asymptotic will work. And in particular, we have this error term here.
Right. So no, the question was for this error term to be actually an error like little o of M, which is your leading term.
Yeah.
That condition is required, that log M by log D goes to infinity.
If you have,
because log M to the 1/3 would just be like of the size of log M.
Yes, right. So, okay, so I forgot. Yeah. So M is growing very fast and D is also growing. Yeah, so thank you. I just got a little confused. So if you have this growth condition, log M by log D going to infinity. So this is a very, very strong condition that allows D to grow like any power of M. Of course, we do want D to be less than or equal to M. So,
okay, maybe since we are, it's almost time for the next talk, maybe we can thank Kaneenika now, and if there are any other questions, I think maybe we can discuss that later. Right? Thanks.
Yeah, Manjunath, Neha, I will write to both of you about this.
Sure.
Sure, thanks.